Hey guys, can I get a sound check?
Yeah, I can hear.
You can sound good.
Hey, this is cool. We have a Lord turnout today. Is that good or bad? Hey.
For part number, what is that, 4? Getting an RN of like 3.9 to times 10 to the negative 4. It's like way off, but that's exactly what I'm getting from the simulation. Is that something to be concerned about?
Yeah, that's really small. Wait, so
Yeah.
hold on. You're getting a R sub n of 2 times 10 to the minus 4 ohms?
No, a 3.9 times 10 to the minus 4, but still, yeah.
Yeah, that's still no. I mean, you should be getting like sort of kilo ohms.
Yeah.
Hmm.
And when I did the measurement or the difference between them, so like my my rising time and falling times, those were my rising time for h equal to 3 was 3 times 10 to the 11 to the negative 11. And then for the rising time of h equals 4 was 3.4 times 10 to the negative 11. So they're pretty close together. So it was like
that's reasonable. So that's wait, so this, but the rising time would give you R sub P, wouldn't it?
Yeah, my R sub P was like 9.7 times 10 to the negative 4, which was still super small.
Huh. What?
I don't know if I did the math wrong, but I basically, I subtracted those two, and that gives you like 4 picoseconds. And then I basically divided that by the 3/2 times CG that we got previously.
Yeah, let's do that real time. Let's see where we get wrong. 4 picoseconds is 3/2 R sub PC. And let's
In
see.
my CG I had as 80 femtofarads.
Okay, wait a minute. Now this C is per micron. So you should be using like 1 or whatever femtofarads.
Oh, okay, so it's not, got it. So it's the unit C.
Yeah, let's see if that works out though. Now you got me worried. 4 picoseconds divided by 1 times 10 to the minus 15. Let's see, what does that give us? Well, yeah. Well, okay, let's do this the brave way, right? So let me add this. So it's R sub P would be 2/3, 4 times 10 to the minus 12 seconds. And say, I don't know, what did you get for, let's say two femtofarads?
For
C sub G, I guess.
Basically 2.7. No, that doesn't seem right. Because if I have 80 femtofarads for my CG for the previous number, but then if I divide that by the 28.8 microns, then I get about 2.7 times 10 to the negative 9 for my CG.
Wait. So CG, so you had 80 femtofarads divided by 28.8 microns. Now you shouldn't plug in this because you want to get it per micron, not per meter. So don't do the 28.8 times 10. So it'll be like 2 times 10 to the minus 15-ish or 2.8. But so just to get the order of magnitude, so it'd be 2. So it'd be 2/3, 2 times 10 to the third. So it'd be 4/3 of, so it'd be something like that, kiloohms, which would be good. So I think that's the problem you're having. Does that make sense? Do you want to run those numbers just to see?
Yeah, I think so. So I what I just did is I just changed it to be 80 femtofarads divided by just 28.8. So I basically removed the micron change, and then now I'm getting an RP of 9.7 times 10 to the 2.
Yeah, so like about a kiloohm.
Yeah, so that makes sense now.
That's reasonable. You scared me for a second there.
Yeah, I was like, there's no way that value is right.
Yeah. Whoops. You like a new discovery. Is that how have you started the logical effort thing? Or I guess it wouldn't make sense yet.
No, I'm about to. That's my next task. I was trying to figure out what was wrong with that.
Gotcha. What's your gate?
I believe I'm the 2-input NAND. I think pretty much everybody is.
Oh, everybody's a 2-input NAND? Did I screw up my my customization?
No guarantee on that, but there's probably quite a few. Depends on what year they came in.
Oh, I see. Yeah. See, I screwed this up. I didn't know how they gave you guys numbers.
Yeah, I'm not entirely sure, but there's probably quite a few of us.
Cool. Well, I'm actually happy for you guys because it's like nothing worse than being a 4-input NOR or something like that. Things get really slow. Yeah,
good. There's no way.
Okay, good. Well, I did my due diligence and still didn't screw anybody over. That's good. My conscience is clear. Okay, guys, anybody else or Logan, any other questions about the project? I threw some stuff. I think I put some stuff up on some suggestions or answers to questions, video. I don't know if anybody has any other questions.
Not really. That video helped though with the last part.
Okay, cool. Yeah, I mean, you guys have like another week to to crank on this thing. So hopefully it'll be my just again, I think I've mentioned this before, and given that you guys don't have any unlikely to have funky logic circuits like 4-input NORs or something really slow, make sure that when you guys put this thing together, oops, when you put this guy together and simulate, make sure you're getting like full rail-to-rail signals here. And then basically you do that by slowing this. If you aren't, slow this guy down until you get some clean looking signals all the way at every point, because that's something that like went wrong last couple of semesters is people were just running it too fast and getting really like bogus results. So don't do that. Anything else? If there's nothing else, I'll just go ahead and jump on the sequential circuits. Let's see, what do we do? Oh, I had this slide deck. That guy. Okay, so I put up a recording. I don't know if you guys had a chance to look at it, but it was going through and talking about these, the concept of sequential circuits as opposed to combinational circuits. I won't go through all of it, but let's just say the main thing is, these devices, like these logic elements, like NAND gates, NOR gates that we've been talking about so far, are combinational circuits. They have no idea about what happened before them, what's going to happen after them. They're just whatever input is sitting in their inputs now is leading to outputs. So they're like very zen, they're very in the now. That's all they care about. So if you need your circuit to remember some previous event, an example of this is like a finite state machine where my favorite example, like I gave in the recording, was like a vending machine. It needs to know that you already fed it the money before it says, hey, go ahead and hit the button and select your drink, for example. It needs to know that at a previous time you actually gave it money. So you need some way to have the concept of some event that happened before. And same, and another good example is pipeline stages. I'm sure you guys have, a bunch of you guys have studied that. It's a way of trying to get more throughput in your system at a certain amount of time. And so again, you need sequential circuits to separate those pipeline stages. And so, there's different. So we need to basically look at what these sequential circuits look like. These they're flip-flops and latches essentially. And so, mentioned how, they tend to be really power hungry. The whole clocking sequential circuit deal in like your clocking network in your chip is probably taking up at least 25% of the total power consumption of your chip, because it's a very there's a huge load on your clock. There's lots of these sequential circuits in your chip. They're all seeing the clock, and by definition, so looking at the CV squared F equation for power, or alpha CV squared F, you have the huge capacitance on this node, so that doesn't help. By definition, this is running at the highest frequency, the clock is available in your system, and by definition, the activity factor is 1. So it's basically as bad of a case as you can get in terms of power consumption. So it's huge. So that's one thing that's really important. And the second thing that gets really important is this concept of skew. And so there's this concept of, I don't know what they call it, maybe they call it the theoretical clock. So when you're designing your Verilog code, say, you have a clock. Correct me if I'm wrong. I don't know if what you guys have played with in terms of these HDL languages, design logic, etc. You have a clock that goes to all your circuits. So that's, I forgot what they call it. Maybe it's a notional clock or a theoretical clock, where it arrives in all your flip-flops at this or latches at the same time. But the reality is that the clock is being physically distributed on your chip or FPGA or wherever, and there are short routes, there are long routes, and physically it'll take a while for the clock to get there if you're at the very end of the chip, or depending on, we haven't had a chance to talk about clocking networks, but it could be even other places on your chip. So some places would get your clock edge faster than other places. And this is this variation called skew. And it's a very important part of your design. So the reality is the sequential circuits and clocking take a disproportionately large percent of the power consumption. And it turns out they will also take a disproportionately large percent of your design effort as you fight this thing called skew, which ends up being a big, big problem on every single design, because it's just hard to distribute these clocks. They're running really fast. Your product engineers, your marketing people will always make sure you're running at the absolute fastest you possibly can, 2 gigahertz, 5 gigahertz, whatever. And so your so-called clock unit interval, and imagine if you're like a clock that's running at a gigahertz, okay, which is, we don't even think about, right? I don't know how fast your cell phone processor is running, but a gigahertz clock is a nanosecond period. So I don't know. I'm trying to remember what like your typical PC processor runs at. Say it runs at 2 gigahertz clock. Okay, so that's a 500 picosecond period for your clock period. So the whole thing is 500 picoseconds. So you can't have a huge amount of delay variations from chip. Imagine how easy it is to get. We did some calculations, and the delays through a single inverter in like processes might be 10 picoseconds. So imagine how easy it is to get variations of clock edges from one side of the chip to another, and it ends up being a really big issue. Anyway, the rest of the stuff, I talked about the different types of the specific design of latches and how that's evolved over the years as a way to show what a good latch is, or what problems exist in latches. And then, flip-flop is really, if you want to think of it from a circuit design point of view, internal to the flip-flop, is really 2 latches back to back. You have 1, you have 2 latch. And the difference between a flip-flop and a latch is level sensitive, and flip-flop is edge sensitive. That means if you have a latch, let's see if I had some timing here somewhere. Yeah. So basically, if we look at a clock and some input that's doing something, you look at a latch. So the output of a latch is, as long as the clock is high, in this case it's high level sensitive, the output of the latch is just going to follow the input. As soon as the clock goes low, the input can do whatever it wants, and the latch keeps its previous value until the clock goes high again, and then it'll take the value that's in the input. In the flip-flop case, on the other hand, the output only responds to the input when, in this particular case, at the rising edge of the clock. It could also be on the falling edge of the clock. But basically, the changes on your output data only happen on this rising edge of the clock or always on the falling edge of the clock, depending on how you design that circuit. And generally, I was always like wondering what the big deal is. I don't know if you guys have studied clocks versus flip-flops, but I have in my worldview, latches are bad, evil things, and flip-flops are good things. There's like, it doesn't seem like, well, one is high level, one of them is edge triggered. What's the difference? Well, the main difference I see, well, I've seen lots of problems with latch-based designs. You want to avoid these things like the plague, except when you're running very, very fast. There is, the flip-flop is 2 latches back to back. Okay, so inevitably it has more timing constraints, there's more of a delay, there's more of a timing overhead associated with a flip-flop, just because you have, there's more circuits, more delay, etc. Latch is a lot simpler, so it can go faster. But the problem with the latch is, or anything that's like level sensitive like this, if you're going to have a bunch of them in your circuit, and invariably one of them will do something you don't want it to do, and you'll miss the problem. Something that's edge triggered like a flip-flop, it's a lot more controllable in the sense that you only have to worry about what's happening at just one point in time, okay? Just at this rising or just at the falling edge of every clock cycle. Whereas a latch, whatever is happening in this time, it could easily go through your circuit and screw things up. And so that's something I've seen over and over again. So unless you really have to, just root out all latches from your design and use flip-flops. The second reason flip-flops are good is that, we haven't used a lot of computer-aided design tools, but in a real design, what you would do is you would design, your big digital circuits with Verilog or VHDL. You would synthesize it and do a place and route. And place and route, and then part of the place and route, a big part of it is the clock tree generation for your circuit. And these place and route tools understand flip-flops, and they understand them very well. So, in terms of the timing constraints, etc., they can deal well with edges and flip-flops. I don't know why. Probably for the same reason as I mentioned, there's only one point in time they have to worry about whether stuff gets there or not. They don't understand latches well. So they will screw up latches, every time. So anyway, if you don't remember anything else from this class, I've said this maybe a handful of times in this class, but remember this, just don't use latches unless you're doing it very intentionally, let's say. And, from what I've seen in like Verilog or VHDL, it's really easy to get unintentionally latches depending on how you write your code. So, but just be very, very careful about it. We're still talking, although, I think they're evil. I'm just joking, but like you still end up using latches, but again, very intentionally. Where I think they're useful is, let's say you're designing like a pipeline stage. It has to go crazy fast. The overhead of a flip-flop is just too much. And it's, a small constrained type of problem. And again, you're just trying to crank data through there as fast as you can. Like, go ahead and use a latch. So there's a place for latches, but, it's very, very, to me, it's like a very, very narrow set of requirements. Don't use latches everywhere. And it'll be tempting to use latches because, again, they have low, low overhead. They're physically small. The power consumption's less, but they will burn you. Okay. So then we talked about, in my recording, we talked about these different type of implementations, etc. Now I want to talk a little bit about, so we're going to be talking about the idea of, well, okay, so we have these circuits now. How would we use them? So let's say you had a flip-flop. Again, I guess I'm just going to say the same thing as I just said. Flip-flop is in my opinion, very safe. So I think it's, let's say, safe. And basically, you have your combinational circuit in between two flip-flops, and basically you have to make sure this stuff, basically the output from one layer of flip-flops goes through your combinational circuit, appears in the next flip-flop in this time frame, in this clock period. So this is how much time it has. Plus, you have to worry about some timing overhead. It has to get to the input of this next layer of flip-flops a certain time called hold time. We'll talk about that a little bit before the clock. So you have to have stable data somewhere out here before the rising edge of the clock arrives. And that data has to stay stable for a certain amount of time after the clock arrives, and that's called the setup time. So you have hold time and setup time in all these circuits, flip-flops, latches, etc. Is that true? Certainly for flip-flops, but okay, so that's a flip-flop, safest. Then you have latches with two-phase clock. That is, something that the book likes because it's a way to build a latch-based design without using computer, without using CAD tools. And you can kind of control the fact that, if you have two phases of clock that are completely non-overlapping. So you give this first phase to every other one, and you give the second phase to, again, every other one. So it'd be sort of sitting over here, etc. You can basically make sure that you don't have any overlap and you don't get any craziness with stuff running straight through. So this is something that, honestly, I've only seen this in like universities. People don't really use this method, so I'm not going to talk about it much, but that's another sequencing method. And then they also talk about pulse latches, and I'm not even going to talk about this. I have never seen this in anything I've done, and I sort of polled my friends in the business. They hadn't seen it either, so I think it's for the, I don't know, maybe it's used a lot by people, but I think I'm going to mostly focus on sort of a simple clock sequencing techniques. Okay, so now let's come up with some definitions. Okay, so here, these are for combinational circuits. And so we've talked about this already. We've got prop delay and contamination delay. So what does that mean? So let's say you have a certain input and a certain output, and so the input does something and this changes the output somewhat. The prop delay is the longest delay where the output could change. And the contamination delay is the earliest delay where something could change. And again, an example of this was let's say NOR circuit where you have I'm sorry, a NAND circuit would be actually a better example. So you have more than one way, either there's only one way to go low, which is both inputs. If both inputs go high, you go low. So there's only one way to do it, but there's more than one way to go high. You could either have this guy on, or you could have this guy on, or you could have both of them on. And if you have both of them on, you go high a lot faster than theoretically twice as fast, I guess, as if you had only one on, meaning that you could have a very fast rising transition and a slower, well, I drew this backwards. You could have either a fast rising transition or a slower rising transition. The slower one would be your prop delay, and the fastest one would be your contamination delay. Okay, so remember that. And it's always seemed to me like, hey, why do I need to worry about contamination delay? Because the real problem is the prop delay. We want stuff to happen as fast as possible. And we'll see why contamination delay has its, stuff happening too quickly has its own problems. Okay, so anyway, that's the combinational circuits. And then these are all the timing definitions of sequential circuits. Okay, so let's look at these in the case of a flip-flop. Here's your clock, and here's data transitioning before and after your clock edge. Let's say it's a rising clock sensitive flip-flop, and then here's your output Q. Okay, so like I mentioned, the data has to appear a certain amount of time before the rising edge of the clock, and it has to be stable for this flip-flop to work okay. So the data has to arrive a certain amount of time before the clock. That's called the setup time. And it has to stay valid for a certain amount of time after the clock edge. Has to stay. It's if you start messing around with the data here, you're going to get bad data going through. So you have to arrive a certain amount of time before the clock edge. That's called setup. You have to stay valid for a certain amount of time after the clock edge, called the hold time. Okay. And so what this means is there's a couple of different delay elements. One of them, you basically have, because the data is stable before and after the clock edge, you can have, it's all about clock edge to the output, okay, the delay. So you can have a prop delay from the clock to the output, or you can have a contamination delay from the clock to the output. And those are the only definitions, because you got to hold D valid. So D is by definition not transitioning around here. So there's no delay per se from D to Q. And so you just really have clock to Q delays, contamination delay or prop delay. Okay. But latches are a little bit different. So for latches, the data could be changing while the clock is high, meaning that not only could you have the clock to Q prop delay and then contamination delay like you do in a flip-flop, but you could also have the data going from data to Q prop delay and then contamination delay, because the data can transition while the clock's high, and there is a certain delay between the data transitioning and the output changing. And there's a high, there's a max and a min. And then furthermore, your data has to stop transitioning a certain amount of time before the latch closes. So the data has to be stable a certain amount of time before the latch closes, and that's called the setup. And it has to stay, shouldn't change any after the latch closes down, and that's called the hold time. Again, if data is changing around here, there's a chance that unintentionally it'll get through your latch before it fully closes. Okay, so there's more timing definitions in a latch because you have this data to queue delay as well as the clock to queue delays. Okay, so those are the definitions. So like I mentioned, so basically you have to worry about two things in either flip-flop or latches. So you have to make sure that your this is the prop delay through your logic elements. You have to make sure, one, that it's not too high. This prop delay is not, I should say the delay. You have to make sure you propagate your, sorry, you have to make sure your delay is not too large or too small. So first let's look at a case where the delay could be too large, or the maximum delay that you could have in your combinational circuit given a certain clock period. Okay, so it ends up that's, I won't go through the analysis, etc., is the prop delay from clock to queue of your flip-flop plus the setup time of your flip-flop. So, I guess you can see it in this drawing. So let's say your clock edge goes high, right? So you're from this point, there's a change here. So that's when this happened. So the latest that change can happen is the clock to queue prop delay. Okay, that's the latest change that this Q1 can appear on the input of this combinational circuit. And then whatever this thing does, whatever this Q1 does through your combinational circuit, and whatever result appears in this D2, better happen at this D2 before this next clock arrives at F2, and that's the setup time. So that's why the maximum propagation delay you can have in your combinational logic is this prop, is basically your total clock period, right? That's the total time you have. And then you have to subtract the prop delay from clock to queue of this flip-flop. And then you have to subtract out the setup time you need to set up before this second flip-flop. Okay, so this is your maximum delay that you can allow. So let's say you realize, hey, my prop delay through this combinational logic is too high. What are your options? Well, if you figure out before you tape out your chip, before you send out your chip to be built, is you can break this up. Maybe you realize, look, I gotta put this into 2 layers of combinational and sequential logic. I gotta pipeline this guy because it's too much. I've got too much stuff in here. So I gotta cut down the delay. Or maybe you change your combinational logic design. We talked about how you could try to optimize the speed or change the functionality. Look at the worst case paths and adjust them somehow. Okay, so that's one option. And then the second option is, like, it's not a great option, but at least means your chip will work, is let's say your chip comes back and you realize your things aren't working and your max delay is too much. Well, the good news there is that you can reduce your clock speed. So it means you can increase your clock period and still get your chip to work, right? So if you notice that this prop delay needs to be less or equal to the clock period minus this amount, meaning that if somehow you made a mistake and you were looking at a clock period of 500 picoseconds, your chip's hosed up, and you can change that to 550 picoseconds and your chip works. So it's not the greatest thing from a marketing and sales perspective because your customers are, expecting a certain performance, but at least you have a working device. Okay. So as you'll see this, so there is a case where that will not be true, which is really a bad case scenario. Okay, so let's look at latches, which is maximum delay of latches in a two-phase latch system. Do I even want to bring this up? You know what? I'm not even going to talk about two-phase latches. Forget it. Should I talk about two-phase latches? Okay, let's talk about two-phase latches. I don't know. You guys aren't going to see this in the industry. Okay, but I will talk about it. So, a two-phase latch system, you have, I'll just maybe just mention it. So you have the prop delay associated with the sort of the first phase and the second phase logic. So that those two have to be less than the clock period minus the prop delay from Q1 from D to Q for the first latch plus the prop delay from D to Q for the second latch. So assuming those are equal to 2 times prop delay Q. So this is what ends up here. Okay, so that's the maximum. This plus this, excuse me, has to be less than this minus these 2 prop delays for the latches. Okay, now this one, again, I haven't run into this. I'm going to talk about this one. Okay, so that was, let's go back to the flip-flop. So we talk about the maximum delay. Now let's talk about the minimum delay. So this is really a bad situation because let's say if somehow this delay, let's say these were just, imagine if you just didn't even have this, you just had a shift register, right? The data from one clock going into another clock. So what can happen is the data from this guy, if you're not careful, the data from this guy can race through here before the next clock. If you violate your hold time, right, means that your data is not stable for a hold time before this clock. This data can actually race through to the output of the second stage of this flip-flop in the same clock edge. Okay, so, and that's really a bad situation because what happens is, like I mentioned, if you got a maximum delay problem in your flip-flop, that means you have a sort of a setup delay type of problem. It's not good because you can increase, it's not good because you won't meet your clock frequency specification, but at least you can get a working chip by making your clock longer. At least you can debug your chip, if nothing else. Maybe you can negotiate with your customer to buy your chip as it is or something, maybe give them a discount. I don't know. But in this case, if the data is racing through on one clock edge, because it's a clock edge problem and it's the same clock edge, there's nothing you can do about that. You're just going to have a non-working chip. You have to go and redesign your chip. You can make this clock period as long as possible. It doesn't matter. If it's the same clock edge where things are running through, it just, your circuit still won't work. And this is like a hold time violation. And it's really, really bad, obviously, because you can't do anything to fix this. Okay, So this is why, this is where sort of the contamination delay comes in, because you could have a situation where you have the clock to Q contamination of this guy, plus the contamination delay of this guy. Everything is too fast, and now again it races through. Okay, so basically you have to make sure that the contamination delay of your logic is larger than the hold time minus the flip-flops clock to Q contamination delay. Okay, and I can't emphasize this enough. This is really, again, a situation where it's, you know, you'll see it. We haven't gone into testability, but again, if you guys get into chip design, you have these things called scan test in your chips, which are very commonly used. And you basically, long story short, you put all your flip-flops into this test mode where they get connected. Just during the test mode, they get connected in the shift register type of sequence. And so you got basically, you know, flip-flops are just connected up again. The shift register means they're just going directly from one to the other. And if you screw that up, you just get a non-working chip, non-working testability, which is, you know, back to the, you know, it sets you back a couple $1 million and a year. So the two-phase latch, again, I won't keep saying that I'm like not a big fan of this idea, but the contamination delay there has to be more than the hold time minus the non-overlap time minus the clock to Q contamination delay. Okay. And we won't talk about pulse delay. I'm not going to talk about time borrowing for. Okay, so now we're going to talk about clock skew, which is, again, it's kind of gets important. So the clock skew, again, is the uncertainty in the arrival time a clock. Okay. Now, what does that uncertainty mean? So if you actually look at a physical clock on a chip, you'll see two types of uncertainty. One of them is, you know, like I mentioned, you'll see some, like, you know, position 1 on the chip, and then there's position 2 on the chip, and the clock won't arrive at the same time. There's some delay between those, whatever that is, and that's called the skew between these two arrival time of these clocks. And it could be that things be arriving too fast or too late, and there's a bunch of stuff that comes into this, right? So this could be like the same for all your chips. It could be different for each chip you get out of the foundry, because, you know, they'll have some small variations in delay. It could be it's like they changes over temperature, because your delay through your, you know, if there's a certain number of buffers that are, you know, the clock network is going through before hitting this guy, that delay changes over temperature or over supply. So those are the possibilities. The other uncertainty, which we won't talk about, but you'll be hearing about, you know, as you guys go to work, etc., is jitter. And jitter is a time varying uncertainty. So if you actually look at a clock on your scope and you zoom in, is, you know, there'll be this thing will not always arrive at the same time. There'll be sometimes it'll come a little bit earlier, sometimes it comes a little bit later, and this is a function of what's generating the clock. There's some is usually a feedback loop. Again, won't get into this too much, but there's this variation in when the clock arrives. And again, when you're talking about a 2 gigahertz clock, it's easy to get tens of picoseconds of variations from clock to clock edge, depending on how you generate your clock. And by the way, like 2 gigahertz isn't the maximum clock that you can have right now. In the high-end Xilinx parts, you can get 56 gigabit per second of data transmission. Not all of it is, they use multi-levels, et cetera, but you can just imagine the kind of timing constraints you have at 56 gigabit per second. It's tens of gigabits per second in very short times. So anyway, we're just talking about something that's constant here. So, which is this uncertainty, but we're not talking about jitter. So this clock skew is this uncertainty you get because not all your flip-flops see the clock edge at the same time. Okay, so that uncertainty has to get added to your budget, meaning that, again, the maximum amount of time, the prop delay that you can have in your flip-flop circuits, you have to add the maximum skew that you're allowing to that. Before we just had this as what we're subtracting. Now we had to add the skew. And notice what this is doing. This is saying that you can do even less in this combinational circuit. Whatever this uncertainty is and the arrival time of the clock across your whole chip is eating into your timing budget for the maximum amount of time. Okay, so I think that's the issue there. And notice it's kind of doing the same thing here. Okay, so skews a lot of times sets the limit to your operation. So in effect, what happens is when you do the design, the way it actually works is you agree on, maybe with yourself or with the rest of the design team, as to what's the worst case skew that you can allow in your chip. And then your timing, your place and route tool will place the logic, and then you run a timing analyzer on the final result, and it'll tell you that you've missed your timing. So it'll give you like, here's 1,000 paths or whatever number of paths where, because of clock skew and delays, etc., you don't meet your timing. Okay, it skews too much, and now you have to go. You go through every one of those paths, and you got to have an answer for each one. Either you change your combinational logic, or you change your clock network to reduce the skew in that particular path and hope that you don't add skew to another path, etc. So that's how that works. But that's where the skew comes in. I'm not gonna, anyway, so it does a similar thing. Again, you have to add these two-phase latches. I got to take these out of my view graphs because I just don't believe in this approach. But anyway, you have to add the skew. You have to add the skew here as well for the prop delay. And I'm sorry, the skew doesn't really affect your prop delay, but it does affect your contamination delay in this two-phase latches. But again, I don't think it's like really a viable option. This is like some propaganda by why two-phase clocking is good. Nope. Nope. Okay, so here's just the summary of the other stuff. I think I'll leave it here. Is that so? I think flip-flops, or I just want to emphasize to use flip-flops to, especially if you're using timing tools, avoid latch-based design as much as you can. With flip-flops, it's important, make sure you worry about the hold time, the minimum delay. Most people tend to ignore it and focus on maximum delay, which is of course important because that sets your slowest clock you can have. But the minimum delays are also more dangerous in some ways because you can really get the non-working chip. So use flip-flops, worry about a hold time delay, and the last thing you want to remember is that skew, is going to exist. Clock skew is going to exist in all your designs just because physically it takes time for a clock to get to all the different points in your circuit. And that, that's probably you're going to spend a significant amount of your design time trying to deal with that skew. So I will stop it there. And, I think we can just, guess that's the last lecture for the semester. So do you guys have any questions before I let you go? Sorry? Oh. Salvador, did you have a question?
Yes. You will have office hours during the final week, right?
Yeah, you know what? So finals week, if you guys need to get a hold of me, just shoot me an email and we can just, I can try to free up some time. So we can talk.
Okay, sounds good.
Sure. Anything else, guys?
Nope.
Nope. Okay, guys. Well, have a good luck with your project. Let me know how I can help if you're running into problems. And yeah, have a great summer. Well, if you're gonna get a summer, I guess some of you guys will just go straight to work.
Yeah.
Make if you do, I guess make money. That's like a good idea. Thanks, guys. Take care.
Have a great one.
Thanks. Bye.